One of the important parameter in deciding the performance of the alternator is voltage regulation. Basically, the voltage regulation is defined as it is the ratio of, and it is expressed as shown in the slide. Voltage regulation is equal to no load voltage minus full load voltage divided by full load voltage. So this can be used to compute the voltage variations in the alternator from no load to full load. Actually, the percentage of voltage regulation should be lesser, but based on the load connected with the alternator, the voltage regulations of the alternators is varying. But it should be in the minimum value, so then only we can say that the alternator is good. And to find the voltage regulation of an alternator, we are using different kinds of methods. Direct loading method and synchronous impedance method, which is called as EMF method, and ampere turns method, which is called as MMF method, and zero power factor or Portier triangle method. Then ASE modified of MMF method and two reaction theory. So based on these available tests, we can find the voltage regulation of the alternator. And what causes these voltage fluctuations or voltage variations in the alternator terminals? In the previous video, I have posted the armature reaction, and we know that there are three kinds of loads connected across the output terminals of the alternator, and generally we are connecting two or three different kinds of loads with the grid. So resistive load, so that creates unity power factor, and inductive load which creates lagging power factor, and capacitive loads which creates the leading power factor in the alternator terminals. So when you are connecting the resistive load across the output terminal, so that causes the unity power factor, and that creates cross magnetizing effect in the machine. So you can see that here there are two axes, one is x-axis and the another one is the y-axis. In the x-axis we are taking the armature current or the load current, and in the y-axis we are taking the terminal voltage. So this terminal voltage is represented by the letter V, so that V can be expressed as Eg minus the total voltage drop in the armature winding of the alternator. Here minus armature reaction. So terminal voltage can be expressed as, and it can be computed from V is equal to Eg generated EMF minus voltage drop in the armature minus armature reaction drop. So this armature reaction drops is playing the major role in deciding the voltage regulation of the alternator. So when you are connecting the resistive load, so there will be a small voltage drop due to the armature reaction in the machine. So this can be shown here. So this can be seen here. And when you are connecting the capacitive load, we know that the resultant flux pi r will increases with increase in the armature current. So you can see that when you are connecting the capacitive load across the output terminals of the alternator, we can see that the terminal voltage of the alternator is greater than the rated voltage. So this is due to the magnetizing effect in the alternators. And another one is inductive load. And when you connected the inductive load across the alternator terminals, it creates demagnetizing effect within the alternator, and that leads to the reduction in the huge voltage drop due to the demagnetizing effect in the alternator. So that reduces the terminal voltage hugely. So there is a large difference in between the rated voltage and the full load voltage of the alternator. So that leads to more voltage regulation, and that shows that that generator is improper and it is not suitable for the applications. So that should be known that before going to use the alternator, we have to calculate the voltage regulation of the machine in order to utilize the machine properly. Thank you.